a simple truss system as shown in figure. So here, if you clearly observe now, the cross section of the members, they are different, and a point load is applied at this point. They specified the material properties. So they specified Young's modulus as 210 gigapascals and Poisson's ratio as 0.25. So we need to find the reaction forces at the pin joints and also the displacement along the truss members. So the first thing is you need to interpret the problem. So once you have a problem, you need to simplify that. So generally, if you want to solve any problem using any finite element methods, software based on finite element methods, generally you follow a certain process. So we divide the process in 3 steps. First step is pre-processing. Second step is solution, and we end with the post-processing. So in pre-processing, you need to define the problem. You are using the software, and manually you need to do it. So the first step is you need to define the type of element. So here element type depends on the type of problem. In our case, since we are solving a structural problem now, and we are related to truss system, so you can use line elements or like bar elements. If you speak theoretically, generally we use bar elements to simulate a truss member. From one software to software, the name of the elements they change, but the properties will remain same. You need to define real constants. So in this problem, you need to define the real constants, and we consider the area of cross section as constant, and we define area of cross section as the real constant. Next, we need to provide the material properties. You need to create the model, then mesh the given model. After meshing, you need to apply the boundary conditions. So these are the steps that comes under pre-processing. And after performing pre-processing, you need to solve the problem. Solution is nothing but once you theoretically speaking, after you get the global stiffness matrix, we apply the boundary conditions and we try to solve it. So the solution part is done by the software. So you need to just create a step, a load step, and you need to define the type of analysis, and the system is going to solve automatically, or the software is going to solve it automatically. So once you get the results will be stored, and in the post-processing, you can view the results. Like you can view the deformed shape of the truss members. You can also view the contour plots of like stress distribution or the deformation along the span, and you can also list the results. So if you take any problem, so these are the 3 basic steps: pre-processing, solution, and post-processing. So we divide the problem into 3 steps. Okay. So let me start with pre-processing. So if you clearly observe here you have 2 members. I consider this member as 1 and this member as 2. So you have 2 truss members. These 2 ends are fixed, or you can use like assume it as pin joints, and you are applying a point load at this point. Okay. So under pre-processing, we start with the type of element. You need to define the type of element. As already told, we are going to use bar elements. In ANSYS, we use link 180 elements. Okay. These link 180 has a property which behaves like a bar element. So you can convert this into a 2D problem. No, each member will be a 1D member, but they are distributed in 2D space. You can also use 3D if needed. Okay. Here they clearly specified the Young's modulus as 210 gigapascals and Poisson's ratio as 0.25. So using this value, you can actually define the material property, and you need to consider it as an elastic material, linear, elastic, and isotropic. So for an isotropic material, it is enough to define Young's modulus and the Poisson's ratio. I will discuss about the other materials later. So first, we start with, so we need to define the element as bar element. I'm assuming link 180. After that, see here in this problem, I can actually the area of cross section is mentioned here. We assume that the area of cross section along the element is constant. So instead of modeling a 3D member now, I will draw only a line and I will define the area of cross section as a real constant. So the area of cross section along this line will remain constant. So here, if you closely observe now, the area of cross section of member 1 and member 2, they are different. So you need to define two real constants. So real constant 1, I assume it as 100 square millimeters, sorry, 1000 square millimeters. And as real constant 2, we allot 750 square millimeters. It is given in the problem. Once you define the real constants, you need to define the material properties. So here I am going to use, since you have only limited data, they provide you with Young's modulus and the Poisson's ratio. So using this data, you can only choose linear elastic isotropic material. Since this problem is structural, you can use structural, linear, elastic, isotropic material, and you need to provide Young's modulus. Generally, it is represented as Ex. So you need to remember that in SolidWorks, it doesn't follow any units. Sorry, in ANSYS. So you need to consider the units, or you need to follow you need to have consistency. Like if you are specifying lengths in terms of millimeters, all the lengths should be specified in terms of millimeters. Similarly, if you want to specify, once you specify the lengths in millimeters now, you need to specify the Young's modulus in terms of newtons per square millimeters. Okay, so you need to convert gigapascals into 210 gigapascals into Newton per square millimeters. So there is no problem with the Poisson's ratio. It doesn't have any units, so you can consider it as 0.25. So after defining the material properties, you can move to the next step. So here we are going to create the model. So since it is very simple, you can use the modeling tools available under ANSYS to create this model. If the model is very complicated, then you can model it using any CAD software and you can import that into ANSYS. So here I'm going to create the model. So initially, so to model this now, I need to create 3 key points. This is key point 1. I consider this as key point 1. This is key point 2, and this is key point 3. So to create key points, you need to specify the XY coordinates of the key point. Okay, X, Y, Z. If you want to create it in 3D space, you can also use Z coordinates. If you don't want, you can simply leave as space, so it will consider as 0. So if you clearly observe now, I consider this as key point 1 and I allot 0, 0 like this. So this is key point 2. So naturally the coordinates will be 1000, 750. And key point 3, it should be 0, x value should be 0 and y value is 750. So you need to create 3 key points. After creating these 3 points, using those 3 points, you can create lines. I assume each this member, or I will use a line to represent this member. You can name it as L1. So line 1 will be created between key point 1 and key point 2. Similarly, line 2 is created between key point 2 and key point 3. Okay. So once you create the model, this is very simple and you can do it very easily. After creating the model, you need to discretize it. Discretization is nothing but meshing. So generally, since you are related to truss problems, no, we assign each truss one element to each truss member. You need to remember that. So definitely, you need to assign only one element to each truss member. So in this case, you have only 2 truss members. So total number of elements should be 2. You can use size controls and you can specify the number of element divisions and you can specify it as 1. So if I select this line, no, so the line should have only 1 element. So that's why I specified the number of element divisions as 1. Similarly, for this element, the value should be 1. After discretizing or meshing, you can move to the next step where you're going to apply the boundary conditions. So it is always better to apply the boundary conditions on the nodes. Once you create elements, no, automatically nodes will be allotted. So for this problem, you can consider, you need to fix these 2 ends, no. So I select these 2 nodes and you can apply deformation along x, y equal to 0. You can simply select all the degrees of freedom and put it as 0. So you can constrain all the degrees of freedom at a time. As a second boundary condition, I need to apply a load. A load will be applied on node 2. This is clearly observed here. So the value should be, once again, since I specified Young's modulus in terms of Newton per square millimeters, you need to specify the force in terms of newtons. So that's why I need to convert this value into newtons. So since it is acting in the downward direction, see, I consider this as 0, 0 now. So it is acting in the downward direction. So Fy is nothing but it's the force vector acting in y direction, and it is equal to 1500. So I converted this value in terms of newtons. So once you apply the boundary conditions, you can actually solve it by creating an analysis file, and using the current load step, you can solve the truss problem. So I hope you understood the procedure. So now let me introduce the software to you. Are you able to understand? If you have any doubts, you can put it in the chat box. Any doubts? Can I proceed?
Yes, sir. Yes, sir.
Okay. So I want to introduce ANSYS mechanical APDL. So to open the software now, you can use, yeah, you need to use the launcher. So this is the best way to open the software. I'm using mechanical APDL to solve this problem. Okay, so I'm using this product launcher. Let's click this. Actually, we are using server-based software, so you can open it when you connect to the server. So once you click that launcher, no, so you'll have a window like this, and here you need to specify the working directory. You can create a folder, and you can show the path by using browse option. Okay, so I'm using I created an ANSYS work directory. It can be anywhere, and I'm giving a name like this is a exercise 7 no, from our manual no. Exercise 7. You can also name the job. So I mean I'm naming it as DX. So since you didn't create a folder no, so once you click run, so here you have option run. So once you click run, it will ask you whether to create a new folder or not. If the folder is already available, it won't give a warning. Okay, I didn't create example 7. I want to create it, sorry, example 7 folder. I am going to create it directly from this. Let me click run. I'm selecting this. See, it is showing an warning. So stating that it doesn't exist. Exercise 7 doesn't exist. So it is asking whether to create the folder or not. So I want to create a new folder. Why I'm creating new folder is when you solve the problem, no, it will create some supporting files. So if you don't specify a folder, it is always better to allot a folder for a problem, so that all the supporting files will be stored in that folder. So that's why I'm creating a specific folder. Okay, let's click S. So then it will open the software. So this is the graphic user interface of ANSYS APDL. We are using 16 version. Student versions are available. You can go into ANSYS website and you can download the student version. It is free for the students. You can get the latest version. So always remember that you don't have undo option in SolidWorks. So it is better to, once you do anything, no, if it looks good, always save it. Okay, after performing a step, better to save it. You don't have undo. You can't move to the previous step. Okay, to save the database, you can use this option save DB. DB is nothing but the database. Here you find resume database. Once you press resume database, no, you will move to the step where you previously saved. Okay, you lose the information if you don't save it. It will move back to the last step where you saved the file. So quit is to come out of the software, and this is the main menu, and here you can find different options. Okay, as already told, we divide the problem. So we use 3 steps now. First step is pre-processing. It is specified here, preprocessor. Second step is solution, which is specified here. And the third step is post-processing, which is named as general post-pro. Okay. So initially, you can set the preferences. like solid ANSYS is a very vast software. You can have so many applications like CFD applications, thermal, electrical, and so on. So since we are related to structural analysis, I need to set the preferences. So let me select preferences. See here you have so many options. So I'm using structural. So once I pick structural, no, only the options that are related to structural will be available. So it will filter the other things so that you don't get confused. Am I clear? So I'm using structural option here. Then click OK. So now I will start with pre-processing. Initially, see under pre-processing, you have so many options. I will start with element type. Let's select the element type. To add an element or to delete it, you need to press this option, add, edit, delete option. Let's select this. So since you didn't create any elements, this seems empty. And to add an element, you press add option. Okay. So since you opted since you consider the problem as structural, no, under preferences we specify it as structural. So it is going to only display the elements that are related to structural problems. Okay. See, these are the different elements that are used to solve a structural problem. It clearly specifies only structural element types are shown since you pick that as the preference. Okay. So under structural, see you have different options like link, so truss or the bar problems can be solved using link option, link element. You can select beams. Once again, you have different types like two-noded beam or three-noded beam. Okay. Similarly, if you want to consider as a 2D problem, you can also use solids like 2D two-dimensional, four-noded element. It is quadratic. And sorry, quadrilateral. Quadratic means the elements have mid nodes. Okay. So quad for node 182 represents a 2D element with 4 sides and nodes at each corner. And if you opt for quad 8 node, no, so it is quadrilateral, but it is quadratic element. Quadratic means it has mid nodes. Okay. So similarly, you can also, if you want to solve 3D problems, you can go for solid brick element. Okay. Brick element has 8 nodes. And if you want to go for quadratic mid nodes, then you can pick brick 20 node. Okay. So depending on the type of problem, you need to pick a particular element. Okay. So you need to always analyze the problem. Then only you need to try to solve it. Okay. So I'm considering, since this is a truss problem, no, I'll consider link element. Okay. I'm using this 3D finite strain 180 or link 180 element. Let's select this option. Click OK. So once you select no, an element will be created. So according to it, so it says type 1 and the element name is link 180. So since you have only 2 members and both the members are truss members, I can select link 180 once. So in a problem, you can have different elements, different types of elements. So in this particular problem, there is no need to pick other type of elements. So we stick to only link 180. Then close the window. Now I'm done with defining the element type. Now I'm going to create the real constants. Let me select this option. So actually, as already told, if you clearly observe the problem now, so here the area of cross section is 1000 square millimeters, and the area of cross section of this member is 750 square millimeters. So the cross section is varying from one member to the other member. Okay. So I simplified this problem. So instead of creating a 3D, okay, everything in nature is 3D, but you can simplify it for our convenience. You can simplify it into 1D or 2D. So here I'm considering this truss member as one dimensional. Okay. And we are distributing these one dimensional elements in 2D, two dimension, 2D, no? Okay. So each node, I hope you studied FEM, no? You are studying FEM. I hope you understood that. So each node, if it is 2D, if you are considering it as 2D, no? Truss in 2D space, each member should have how many degrees of freedom? 2 degrees, no? Displacement along x-axis, displacement along y-axis, or you can specify it as UV. Okay. You don't have rotations in truss members. Okay. So we always assume that in truss member, the deformation will be along the axis, and also the forces will be also along the axis. If you consider it locally, okay. So I'm converting this 3D member into a 1D, and I assume the area of cross section as constant. So I'm only specifying the length, and I consider area of cross section as constant, and we are going to specify that area of cross section as a real constant. So you need to create two real constants, like one should have 1000 square millimeters, the other should be 750 square millimeters. So let me add that value. So here I'm selecting add, edit, delete option under real constants. So I didn't define anything, so this is empty. Let's add a real constant, and I'm adding that real constant to this particular link element, link 180. Click OK. See here, you need to specify the set number. By default, it is going to pick if you don't allot a value. So it starts with 1 and it keeps on increasing. You need to specify the area of cross section. So I specify it as 1000. Once again, you need to specify the values in terms of millimeters. Area of cross section in terms of millimeters. That is area of cross section in terms of square millimeters. Because we specified the length, we are going to specify the length in terms of millimeters. Let's allot a value of 1000. Click OK. See, set 1 is created. If you want, you can rename it. Okay. Let me add one more set, because you have two different cross sections now. Once again, I'm allotting that value to the link 180. Let's click OK. So here I'm going to specify it as 750. By default, it is picking the set number as 2 because you already created one. Click OK. So I'm done with real constants. So we define two real constants. Close the window. Then you can move to the next option. Like I want to define the material properties. Okay. So if you want to specify the material properties, you can use material models. Let's select this option, material models. So once again, since you use since the preferences, under preferences, you defined is structural now. So only the structural option is available. Let's select structural. So I'm selecting linear, elastic, and isotropic. Okay. So if you clearly observe now, under structural, you have different like under elastic materials, no, you have three options: isotropic, orthotropic, and anisotropic. Okay, so to define an isotropic material, two constants are enough, because isotropic material properties along the orientation, no, they are similar. So that's why it is very easy to simulate isotropic materials. So you can get the data from the tensile test. Okay, so I'm using isotropic material. So Young's modulus, it is given, no, 210 megapascals. So I want to convert that into newtons per square millimeters, no. So it should be 210 into 10 power 3. So you can specify it as e power 3. E power 3 is nothing but 10 power 3. And let's add a Poisson's ratio as 0.25. So I'm done with the material property. So only the cross section changes for the materials, and the materials are same. Materials remains the same. Click OK. So if you have different materials, you can create multiple materials. Okay. See here, under elastic, no, you have other types like orthotropic and anisotropic. Okay, to define an orthotropic material, you need to specify 9 constants. Let me check that. See, you need to specify these values: Ex, Ey, Ez. These are the Young's modulus along X, Y, and Z directions respectively. Similarly, the Poisson's ratio along XY plane, YZ plane, XZ plane. Okay, and others should be specified according to the plane. Click OK. And if you want to define an anisotropic material, you need to provide 21 constants. Okay. So generally we get these values by performing experiments. Okay. So it is very complicated. Okay. So generally in nature, most of the materials are anisotropic, but to get these values, it is very difficult. So we take assumptions, and we can convert them into, like, assume it as isotropic or orthotropic. Similarly, you have other options like nonlinear. Here you can use different options like elastic, inelastic. Suppose if you want to simulate a plastic material, you can go for nonlinear, and you can define by getting the values from the test data. You can define the values. Okay. You can also use viscoelastic materials. So at present, we are going to stick to isotropic materials, since they specified only the Young's modulus and the Poisson's ratio. Click OK. So I created a material model, and it is named as number 1. Click OK. So I'm done with the material properties. So after this, I want to create the actual model. So since the model is very simple, I'm using options that are available under ANSYS APDL. Okay. So here, initially, I'm going to create key points. Key points are nothing but points. They name it as key points. Okay. So I want to create key points, and I'm using the active coordinate system. See, I'm drawing key points on this XY plane. Okay, you can, if you want, you can create it in 3D space by just specifying the coordinates, X, Y, Z coordinates. Okay, I'm using active coordinate system. So if you can specify the number, key point number. Otherwise, it is going to pick in a sequence, like it starts with 1 and it will continue. Okay. After you can specify the values here. Like I assume this point as 0, 0, 0, no. See now I'm unable to view that window now. So just press this icon, raise hidden options. Then you will have the window displayed again. Okay. So as a x value, I'm defining it as 0. If you don't specify anything here, by default it will consider as 0. If you leave the boxes empty, okay, so it will try to assume it as 0. Okay, but not the value of for the key point. It will assume it as 1. Okay. Here you have two options. If you press apply, it will create the node, sorry, the key point, but this window won't be closed. If you click OK, a key point will be created, and it will, the window will be closed. Okay. Never press apply, then OK. If you press apply and press OK, using the same values, it will create two key points with same coordinates. Okay. So let me pick. So initially I want to show that, yeah, let me leave it as empty space. I'll just press apply. So a node will be a key point will be created at the origin. So at present you are unable to view that because it is coinciding with this triad. Okay. Then what's the next coordinate? This coordinate should be coordinates of the next point. Key point 2 is 1000, 750. No. So I'm opting. I'll specify the x coordinate as 1000 and y coordinate as 750. I'm leaving the z coordinate empty, so it assumes 0. Okay. Once again, I'm clicking apply. So it will create a node here, somewhere here. Let's check it later. You have one more point now. So I'm creating it as the coordinates should be 0, 750. Okay. Let's click OK. Because I'm done with the creating the key points now. You need to create only 3 key points. I already created 2. So that's why I want to close the window. Click OK. Then it will create a, see here, it is clearly observed, it is 3. Okay. Let me zoom out. When I zoom out, you can clearly observe now this is 2, this is 3, and 1 will be is actually present here. So after creating the key points now, I want to join these key points using lines. So each line will act as a truss member. Let me create lines. So under modeling, use line options, click on lines, then select line. See, lines include arcs and splines. At present, don't bother about arcs and splines. So we are only bothered about the straight line. Okay, I'm opting for straight line. Here you have so many options. You can directly create a line by specifying the coordinates. Okay, but here for my convenience, I'm creating key points, and based on those key points, I'm creating the lines. So I'm opting for line option. See, this window, it is asking us to pick key points. Okay. And here, maximum you can select is 2. Because you can only draw a line between 2 key points, no? You can only pick 2. Okay. So I'm picking, see the arrow. So if it is pointing in the upward direction, that means you are selecting a particular point. Suppose if you want to unselect the point, then you can use this unpick option. If I click it now, see the arrow, it is actually pointing in the downward direction. So that's a major difference, pick and unpick. So let me pick the points. I'm setting this point 1. Then I move near to the second point now, automatically it is showing a preview. Okay, if I move towards this point, see, it is showing a preview. So that means it is just a graphical representation. It is not creating anything until unless you press OK. it won't create a, or until unless you select one more entity, it won't create a line. Okay. So I selected this point. You can clearly observe that yellow box, no, that indicates that you're picking a point. Okay. And here the count, it shows one. We already picked one key point, no? And I'm selecting the second one. Let me select the second one. Okay. So it created a line. Now I want to continue. You can also specify, if you want to create a line, no, you can also specify the key points here. So let me use this window to create the next one. So I want to create a line between key point 2, comma, key point 3. Then click apply. Okay. So it is already creating a line. So don't create OK. Don't click OK now. You can click OK now because I didn't specify anything now. Okay. So since it is already created now, I will say cancel. I'll close the window. So this is how you can actually create lines. Just specify the pick the key points. So the line will be created, or otherwise you can specify the nodes here. Am I clear? Let's close the window. I'm pressing cancel. So I created 2 lines. So don't think these lines are elements. Okay. So after creating the model, I need to discretize it. Okay. That means I want to create a mesh. So to create mesh, you can use this option meshing. Let's select this option. So here, the area cross section of these 2 members is different, no? You can define that the cross section by using mesh attributes. Okay, let's select the mesh attributes. So here, I want to pick the lines and allot a particular attribute to that. So I will use pick lines option because the variation is different now for each member. So I'm opting for pick lines. Okay, let's select this line. Click OK. So now you have this line attributes window, and here you can specify the values like material number. You have only one material, no? We created only one material, so you can under the drop down, no, you have only one option.
Don't do that.
Sorry. You define 2 real constants, no? So when I drop down, here you have 2 options. So real constant 1 is related to cross section 1000, no? So since I selected this line, I will opt for 1. And element type, you only selected one type, so you can pick link 180 as the element type. Okay, let's click OK. Now I need to pick this line and change the mesh attributes. No, let me pick the line once again and click this. I'm selecting this line. Click OK. See, the material number remains same, but the real constant value changes. So I need to allot 750 square millimeters to that particular line. So I'm opting for option 2. Element type remains same. Then click OK. Okay. So here I allotted the real constants and also the material properties to different lines. Now let me mesh. After that, I need to actually define the size. No. So to define a size manually, you can use this option size controls. Let me select this option. If you select smart size, it will create it will pick automatically depending on the type of problem. but I don't want to go for smart size. I'll go for manual size. Let's select manual size option. And here you are going to mesh the lines, no? So I need to opt for lines. Okay. Since I'm going to allot only one element, element for each member, I can opt for all lines. Okay. So that means this size control will be applied to all the lines that you pick. Okay. Or also, otherwise you can use this option pick lines, but you need to individually pick it and add a value there. Okay. So I'll offer all lines. See here, you can provide the element edge length or the element size, or otherwise number of element divisions. Okay. So I don't want to calculate anything. So simply I go for number of element divisions and I will specify it as 1. So always remember that when you solve a trust problem, you need to allot one element for each trust member, not more than 1. Let's click OK. 1. Click OK. See, you didn't actually mesh this. It is only showing the preview. See, since I picked one division, no, so it is showing a preview. So this is one element and this is one other element. Okay. Now I want to create the mesh. I define the attributes and also the mesh size. So it is ready to mesh. So use mesh option. Once again, I want to mesh the lines. I'm setting lines. You can pick it from the graphic window. Click OK. So now you have a mesh. Okay. If you want to actually view the whatever you created, no, you can list or you can plot those entities. See, I want to list the key points. Let's use list option. I want to check whether I did it perfectly or not. Okay, I want to see the coordinates of the key points. See here, you have two options: coordinates only and coordinates plus attributes. So let me pick the second one. Now you created 3 key points. Now see the three key point coordinates will be represented here. See, key point 1 has a coordinate 0, 0, 0. Then key point 2 is 1000, 750, and z coordinate is 0. Similarly, key point 3 has a values 0, 750. So you can, what we did is correct. Okay. Now let me list the lines. You want to list the lines. Once again, I'm using attribute format. Click OK. See, you have 2 lines. This is line 1 and this is line 2. Okay. This number actually represents the lines. You have 2 lines. See, the first line is created between key point 1 and 2, and the length of the line is 1250. Similarly, line number 2, line 2 is created between key point 2 and 3, and the length is 1000. Am I clear? Click OK. You can also view the elements. Let me check the nodes. So I will go for coordinates with angles, or you can opt for the second option, coordinates only. Click OK. See, these are the nodes. You have how many nodes? 3 nodes. So since you consider this element as a bar element or a link element, so each element has 2 nodes. Okay. So for this element, this is node 1 and this is 2. And for this element, this is node 1 and this is 2. Okay. So node 1 is having a coordinates of 0, 0, 0. Node 2 is 1000, 750. So this is node 2. And this is node 3 is 0, 750 because so each test number will be considered as an element now. You can also view the list the elements. Okay. So here I'm opting for elements, attributes, and real constants option. Let's select this option. See, under elements, you have two elements. This is element 1 and this is element 2. So the area of cross section for element 1 is 1000 and area of cross section for element 2 is 750. Okay. So here the material type is same. You have only one material now. So material type is speaking as 1. Type of element is link 180. So it's also same. Type is 1. See, for the first element, it is picking real constant as 1, set 1. And for second element, real constant value is 2. Okay. And the element 1 is created between node 1 and 2. Element 2 is created between node 2 and 3. Okay. So you can use list option and check the model whether you did it correctly or not. Okay. So since this problem is very simple, it takes less than a second to solve the problem. But sometimes if a problem is very complicated and if you without checking all these whether you did it perfectly or not, if you go for solution, no, it takes a lot of time. Like it can take hours or days. And if you make any mistake, no, at the end it will show an error. So it's always better to rectify the problems initially. So if everything is good, then you can go for solution. But still, I didn't add the boundary conditions. Only I meshed the problem. Okay. So total number of elements for this model is 2. This is element 1 and this is element 2. So after this, I'm done with meshing. Let me add the loads. Okay. And define the boundary conditions. Okay. So here I'm defining the analysis type. So this is actually a static analysis, structural static analysis. So you can define the analysis type in solution option, solution step, or in pre-processing under loads. Okay. I want to do it here itself. So let me define the analysis type. I'm selecting new analysis. Here I'm going to pick static analysis. You have different types like transient, steady state, model analysis, dynamic. If you want to find the different types of modes, then you can go for model analysis. So I'll stick to only static at present. Click OK. So now add the boundary conditions. Boundary conditions, we use loads as a step. Okay. So I want to apply the loads. So click apply. Since we are dealing with the structural problem, so only structural is available. So I want to constrain the displacements now at node 1 and node 3. So I will offer displacements. You can apply the boundary conditions on lines, areas, key points, and so on. But it's always better to pick the nodes. If you want to apply boundary conditions, no, apply it on the nodes. So let me select the nodes. Manually, I'm selecting it. So let's pick this. So if you accidentally select this one, if you want to unpick this, activate unpick option, then select that particular node. So it will be deactivated. Okay. So I selected two nodes. Click OK. So now I'm going to constrain all the degrees of freedom, or simply you can constrain UX and UI. Okay. So at present, I'm going for, so since you assume this as a 2D, I mean, the problem is distributed in 2D space, but the answers, it considered as 3D. So that's why I'm picking all degrees of freedom. I want to constrain it. If you don't add value here, it will consider as 0. Okay. So I'm going to fix these two ends. Click OK. So displacement that these symbols no indicates that it is constrained along x and y directions. Okay, z is not visible to you. Am I clear? So now I'm done with the displacements and constrain these two ends. Now I need to apply a force here. No. So I want to apply a force. So under structural, you can use force option. Force or moments. At present, we don't deal with moments because these are all truss members. So truss members are not subjected to. We assume that they are only subjected to axial loads. Okay. So we consider it as the force. Once again, I want to apply it on the nodes. Let's select on nodes option. I'm going to pick this point. So I'm going to apply a force here. Click OK. See if the force is acting along with a particular orientation, you need to resolve that into x, y, and z components. Okay. So, but here in our case, the force is predominantly acting in the downward direction. So that is along fy direction. Okay. So if the force is acting in a particular orientation, then you need to resolve that force into xy components and specify them individually. Okay. So let me select fy. So since this is acting in the downward direction, so this is positive y and this is negative y. So you need to add negative. I'm specifying the force in terms of newtons because we specified Young's modulus in terms of newtons per square millimeters. All the lengths will be specified in terms of millimeters and forces in terms of newtons in this particular problem. If you want to define it in terms of pascals, then the forces should be defined in terms of okay, pascals means Newton per meter square, no? Okay, Pascal is nothing but Newton per meter square. And forces, you need to convert that. Okay. So I'm defining the forces in terms of newtons. Click OK. See, this arrow actually points the orientation of the force. Okay. So let me save the model. So it's always better to save it after creating a step. I forgot to save it, but it is a good practice because if I make a mistake now and if something went wrong and if the window, like the software closes, then you need to redo it again from the beginning. So to avoid that, always better to save the database. Okay. So I'm done with the pre-processing. Now the model is ready to be solved. Okay. So if you have any doubts, please ask me. So what element did I consider as a truss member? Anyone? Mukesh, can you unmute yourself? Mukesh B. I repeat, Mukesh B. Can you unmute yourself? He's only physically present, I think. Next, Manikanta. Manikanta G. Can you unmute yourself?
Yes, sir.
Are you able to understand what I said? So for a trust member, how many degrees of freedom will each node has?
Hello.
Yeah, for a trust member, no? Each node has how many degrees of freedom? Anyone? No, you are not audible. You need to unmute yourself. Anyone can answer. For a trust member, each node has how many degrees of freedom? You are studying FEM now. For a bar element, you need to go through the basics. So in the next class, I will ask you individually. Okay, better to go through the theory part. Then only you can understand. So without basics, you can't perform anything. Okay, let me continue. Are you able to view my screen? So I'm done with pre-processing. So after this, I want to solve the problem. So use solution. I already defined the analysis type now. So if you want to define it, you can also define it under solution. Analysis type as just press new analysis, go for static option. So since this is a static analysis, I'm opting for static option. Click OK. Then you can also define loads under solution. We already did it now under pre-processing. So there is no need to consider it here. You can directly go to solve option. So let me select solve option. And here I want to solve the current load step. Okay, let's select current load step. So it will create a job file and it is going to show the steps. Like, see, everything is displayed here. The type of analysis that you are doing, like problem dimensionality is 3D. Okay, theoretically everything is 3D. Okay, if you clearly see it, no, here it is only 2D. Z we always consider as 0, no, so but still it will consider as 3D. Then degrees of freedom, since you went for link element, no, you will have only displacements along X, Y, and Z directions. You don't have rotations. If you pick beam element, then beam element has 6 degrees of freedom, that is translation along XYZ and rotation along XYZ. So since it is a bar, it behaves like a bar, no, truss member behaves like a bar. So it will have only translations along XYZ because this considering it as 3D, no. So that's why each node has 3 degrees of freedom. But if you solve it theoretically, we only assume UX and UY. So since this is distributed in 2D space, no, you will have UX value and UY values. Then analysis type we defined as static. It is taking steady state. Then automatically it is going to get the global stiffness matrix, which will be symmetric. And if you consider, if you observe the load steps, no, so total number of load steps will be 1. Okay, at 0, everything will be, the force will be applied. In step 1, a force will be applied. Okay, time. So since it is time independent, no, we consider time as 1. Number of substeps, again, I'm taking it as 1. Okay, leave the default values and go for, you can just press OK. I think I made a mistake with the Poisson's ratio. Let's once check it. So move to pre-processing. Material properties, I want to see it is speaking orthotropic. No, I didn't define it properly. Okay. So I will delete this. Poisson's ratio, I will consider it as 1 to 10 GPa, gigapascals. It's converted into Newton per square millimeters. So it should be 210 e power 3, Poisson's ratio 0.25. I accidentally pick it as orthotropic. Click OK. Let me save this. Then move to solution. Use under solve. You can pick this current, you can solve the current load step. Click OK. See, it shows the solution is done. Click OK. Now you can view the results. Okay. To view the results, you need to move to the third step, general post processing. Just select this option. I want to view the deformed state. So if you want to view the deformed state, you can use plot results option. And I'm picking the deformed shape. Let's select this option. So here are 3 options like deformed shape only, deformed plus undeformed, deformed plus undeformed with edges visible. Okay, I will pick the first one, deformed shape only. Click OK. So this is the present. So after applying the force, the truss will be deformed like this, which is shown in the graphic window. So here I can't compare with the original one, no? So if you want to compare it with the original one, you can opt for the second option, deform plus undeformed. Let me pick this option, click OK. See the white model represents the original model, and after you apply the force, the truss members will be deformed, and which is shown by the blue lines. This is the current position. White is the initial position. Okay. So similarly, if you want to view the counter plots, like the stress distribution along the truss member, or the deformation along the truss member, it can be you can use the counter plots to show the deformation. So let me use counter plot. Okay. So here I will offer to show the deformation, no? Degrees of freedom of U, displacement. So I will offer nodal solutions. So under nodal solutions, I will pick degrees of freedom. Okay, let's select this option. You can pick individual components like X, Y, Z components individually, or you can go for the vector sum. So let me pick the vector sum, vector displacement. So it will add all these values, then you'll get the vector sum. So I'm selecting this, click OK. And if you see, this is the deformation along the member. So since these two ends are fixed now, see the value should be 0 here. Blue color represents 0. So naturally, since they are fixed now, you don't have deformation here. And deformation is maximum at this node 2, because a point load is applied now. And you can view the values here. So you don't have negative values because it is a vector sum. So if you want to individually plot the deformations, use nodal solution once again. I want to plot only the Y components. Okay. So let me select this, click OK. So it is 0. So at this interface, it is 0, and this displacement is maximum, but it is in terms of negative value, no? So this displacement is maximum at this end. And here you can clearly, it clearly shows that deformation is, the Y component is 0.04. So since you specified the lengths in terms of millimeters, no, you need to consider this value in terms of millimeters. So maximum deformation is at this point, and the value is 0.041 millimeters, and it is acting in the downward direction. Okay. So suppose if you want to, you can also have a vector plot. Okay. So I will use vector plot. I only consider the translations. So we are not bothered about the rotations. No, you don't have rotations in truss problems. So I'm opting for translation. Click OK. So see, this is the okay. This is the graphical representation. It's showing a vector now. So this the vector, it shows the intensity. Okay. So if you want to view the stress distribution along the members, you can go for element solutions. Okay. Let's select element solutions. So here you have different components. I will opt for stresses, and these are the different types of stresses, like normal stress along x-axis, y-axis, z-axis, then shear stress in xy plane, zy plane, xz plane, and so on. And these are the principal stresses. So generally, for elastic materials, no, you can use von Mises stress. Okay, so I will use this von Mises stress distribution. Let's select this option. Click OK. They're of same color. Actually, maybe the values are near to each other, so that's why you can't differentiate that. So if you want to view if you want to get the theoretical values or the actual values, no, in a tabular form, you can use list option. Okay, so I'm using list option. Now, since we got results now, I will go to results and I'll offer nodal solution because I want to have degrees of freedom or the displacements at node 1, 2, and 3. Okay, so I'll offer degrees of freedom. Click OK. Okay, I'll offer vector sum. Click OK. Sorry, this is under counter plot. No, I want to list results. Okay, nodal solution. Here I want to pick the vector displacement. Click OK. You can get it from the main menu or from here. In the previous case, I didn't pick any option. Only I went for nodal solution. It couldn't understand. Okay. So if you clearly observe now, at node 1, the values are 0, 0, 0 because node 1 is fixed now. So that's why the vector sum is 0. At node 2, displacement along x-axis is 0.0112. Displacement along y-axis is 0.041. Along z-axis is 0. So this is the vector sum. It is equal to 0.043. Okay, and it has a positive value. Vector sum is always will be positive. No, if you clearly observe, no, here displacement along y-axis is having a negative value because it is in the downward direction. Similarly, the values displacements at node 3 remains zeros because it is already fixed. Okay. Now let me display the stresses. So I'm opting for element solution. You can also pick it from here. Element solution. I'll go for von Mises stress. Let's pick that option. Click OK. Von Mises stress is also called as equivalent stress. Okay, S equivalent. So S indicates stress, and S1, S2, S3 indicates directions along X1, 2, X1, XY, and Z directions. So these are all normal stress components. So for the element 1, equivalent stress is 2.5. So stress we express in terms of Newton per square millimeters because everything is in newtons. Forces will be in newtons. Lengths will be in millimeters. So this value should be equal to Newton per square millimeters or 2.5 megapascals. Okay. Similarly, for element 2, this element 2, the value is 2.66. So since they are they're same, no, you can't differentiate much. So that's why in the previous plot, no, in the counter plot, both the elements are represented by red color. Okay, because the values are near to each other. Always remember that in a stress member, stress along the span will remain same. So that's why the value will be same here. Okay. So after this, if you want to have the values related to the reaction forces, you can use reaction solution option. Let's select this option. Okay, and picking all the items. Here only you will have forces along X, Y, and Z. Okay, there won't be reaction forces at node 2, no. So reaction forces only will be at node 1 and 3. Okay, so I'll offer all items, then click OK. See, everything is defined here. Load step is 1, sub step is 1, time is also defined as 1. And at node 1, these are the values fx, fy, and fz. These are the force components along x, y, and z directions. At node 1, force along x-axis is 2000. At node 1, y component is 1500. Okay, z component remains 0. At node 3, x component is minus 2000. Y component is 0. Okay, here we are talking about the reaction forces. And we don't find values at node 2 because node 2 is free to move now. So you don't have reaction forces there. A load is acting. So see, the load is minus 1500 now. So this value is balanced out. Okay. Once again, these two forces will be balanced. So total result will be 0. Any doubts up to now? So you can practice at home. You can download the software. It is free for the students, but only the number of elements that you create now will be constrained. Any doubts regarding this stress problem? So I'll give 5 minutes. If you have any doubts, you can put it in the chat box.